equal to b, that describes a curve in 3 dimensions. We did this way back in chapter 13, a space curve. I don't want just a curve. I want to know what happens if I look at a function of 2 variables. A parametric function of 2 variables. Like those variables are of u, v. And so we're going to end up with 3 functions, of which are functions. Which means that I need 2 domains. I need u and v to be points in some domain D. But what does this actually describe? What is this output? Well, this outputs a surface. This results in a 3-dimensional surface that is defined parametrically. And we call it the surface over D. So D is our domain, and S is a 3-dimensional object, a surface in 3D. An example. So let me think about this. This is defined where u goes from 0 to 2 pi, v goes from -3 to 3. And then I'm going to define points in 3 dimensions based on those values. So let me see if I can figure out what's going on here. Do you want to pick a value for u, or do you want to pick a value for v? We're going to do traces, just like we did when we fixed an x value or a y value or a z value. I'm going to fix a u value, fix a v value. You want to do u first or v first? So pick a value for u. If u is 0, then I have 2 cosine of 0. The cosine of 0 is 1, that's just 2. And that never changes. I have y equals v. We haven't done anything with v. And I have z equals 2 sine of 0. What's sine of 0? Perfect. So let's think of what happens in 3D here. X is 2. Z is 0. But v, and thus y, goes from -3 to 3. What does that describe? That describes a line segment. The y values go from -3 to 3. The x value is stuck at 2, and the z value is stuck at 0. Give me another value for you. Any other value you want. Pi, if u is pi, I'll get an x, y, and a z. Value for x. -2. Value for z. And y is still v. That makes it a free variable, just like it was here. But x and z are pinned, but now they're pinned at another place. So this time I get a different line segment. It's still going in the y direction, but it's way back there. As a matter of fact, no matter what u value I pick, that's going to define a point in the xz plane. And then y is going to go from -3 to 3. So I now know that when I fix u, I get a line segment in different places. What happens if I fix v? Pick a value for v. Let's pick the easiest one I can get away with. What if v is 0? Well, if v is 0, then y is 0. But that means that x is 2 cosine of u, and y is 2 sine of u. Okay, wait a second. That's a shape in the xz plane. Yes, that would be z, not y. Thank you. Helps if I write down the right letter. What's that shape? It's a circle. And it's a circle of radius 2 in x and z. What if I pick v to be 3? What's the only thing that changes? And if v is -3, it's going to be over here. What does this three-dimensional shape look like? Its radius for the circle is 2, and its length is 6. Goes from -3 to 3. What we have actually described, take a sheet of notebook paper and twist it into a cylinder, and you'll see blue lines from your notebook paper going around the cylinder, won't you? Those lines are the curves we did where we fixed v. On the other hand, the margin line here, the red line, that's where I fixed u. We call those the rules, the grid, built into the surface. So in this case, the rulings where I fix U are straight lines, and the rulings where I fix V are circles. This cylinder is made up of stacks of circles laid out in a straight line, or stacks of lines laid out in a circle. Here are my parameters, the U and the V. Am I stacking circles or am I stacking lines? Now, I know the equation for a circle. For a circle. X squared plus y squared equals r squared, right? A circle in x and z is x squared plus z squared equals r squared. If I go back to the equations, x squared plus z squared gives me 4. That's r squared, circle of radius 2. So I could say, hey, let's analyze these like we did our quadratic surfaces back in chapter 12. What was that, September? No, January? It's been a while. But in some cases, that's exactly the sort of analysis I want to do. Same question. If I fix a u value, what do I get? If I pick 0, I get nothing. I get a dot, right? X equals 0, y equals 0, z equals 0. Dot. It's a single point. So pick a positive value. What do you get? In x and y, right? Because x and y have the cosine and sine and v, and that will be allowed to change. But z will be a fixed number. So I'll get a circle up here somewhere. Circle of radius u at a height of u squared. On the other hand, let's fix v. Well, then x and y are number times u, aren't they? Z is still u squared. That's the parametric description of a parabola, t squared, isn't it? Notice if I take x squared plus y squared, the sine squared and the cosine squared give me 1. That gives me u squared. But isn't that exactly equal to z? Hey, z equals x squared plus y squared. That's a paraboloid. Chapter 12, section 6. Son of a... Worked. So here's another way to describe a paraboloid. Now, I will freely admit that some of these get nasty. Oh boy. Let me start this one backwards. Let's fix V. If I fix V, then this constant and this constant are the same. That's number cosine and number sine. That's a circle in X and Y, right? Except it's going up because U is allowed to change. We only fixed V. I have a circle, but it's going up. What do we describe that as? Not a cylinder because it's not a solid. It's just a curve. That's our helix. But I have a helix for every different value of V, don't I? So let me cover up the U's for a second and think about what happens if I let V change. Well, then I've got cosine and number plus sine. That's a circle, but it's moved to a different point because these plus 2 move that sine over, don't they? This shape is a helix, but it's a helix made out of a tube. That circle that we were just talking about is moving up the helix. If I fix a value of V, I get the helix that is the grid line going up. If I fix a value of U, I get a circle going around this tube. They sell this in the Italian markets as a type of pasta, people. This is now a helicoid instead of a helix. Now, I will tell you right now, I do not expect you to draw these things. That's bonkers. On our Canvas page, in the section entitled Grapher Examples, Chapter 16, Section 6, Examples. All of the examples I'm going to do, all of them are shown how to be graphed in our grapher. I don't want you to use my hand. That sucks. But that means for a domain in the UV plane, I describe a surface in X and Y and Z. And that's the connection I need to make here. That a function that is parametric in 2 variables is a surface, even if it's a really complicated surface. And by the way, some of these surfaces they self-intersect. They have pinch points where they're not continuous or differentiable. They have asymptotes in them. They have corners in them. They have folds in them. All of these are describable by these equations. Which means I could try and use the same sort of analysis we just did to figure out which one is which. On the other hand, some things that I already know surface equations for are easy to describe. Do I have that with me? Yes, it's in the other box. Imagine you have a plane in 3 dimensions, right? A plane. I have defined a point on this plane, P0. I have 2 vectors in this plane, from P0 to P1 and P0 to P2. I could make a grid out of those vectors, couldn't I? 2 vector 1, 3 vector 1, 4 vector 1. I could make graph paper that instead of having little boxes would have little parallelograms on it because these are tilted. But what that means is I could say, oh, the plane consists of any multiple of this vector and any multiple of this vector. That allows me to reach every point on the plane, doesn't it? As long as S and T can be any real numbers. Wait a minute, that's exactly a parametric description. This is exactly R of ST instead of U and V. I don't care what letters you use. This is a plane. Only instead of describing it in the vectors using the cross product, using n dot x minus x0, y minus y0, the way we did back in chapter 12, I can define it now in terms of S and T. A sphere. I'm going to be particular. Let's do a sphere of radius 1, the unit sphere. What is the equation for the sphere of radius 1? What's the equation for that sphere? That works perfectly. But if I wanted to graph that like a surface, wouldn't we have to take z equals? And that's going to screw me up, isn't it? Because I'll have a positive square root and a negative square root. I don't want to do that. I am going to think differently. I am going to change my perspective. We have another coordinate system. Let's do this in spherical coordinates. In spherical coordinates, this is the easiest equation on the face of the planet. Rho equals 1. Yes? And theta can go from 0 to 2 pi. And phi can go from 0 to pi. Wait a second. I have a range for 2 variables, don't I? What are the equations for changing spherical back to x and y? And those are on your formula card for the last exam.
P squared sine something.
I had something in there. Let's find it.
X equals like P sine. X equals P sine. Or P sine. The one that's like this.
This one.
Yeah.
Phi.
Phi. Cosine theta. And y equals P minus P sine theta.
And then z equals?
P cosine.
But we said that our radius was 1. Hey, look at this. That describes my sphere in 2 variables, theta and phi. Go out a distance of 1, go around and up to down. The grid lines are lines of latitude and lines of longitude. No, because I only go from up to down. Because I can do that on this side and I can do that on this side. I don't have to go all the way around. I have to go halfway around the ball and then all the way around the ball once. If I already went all the way around in theta, I only have to go halfway around in theta. which now means I can describe with a function both the top and the bottom of the ball at the same time. Only it's not a function of x and y, it's a function of theta and phi. The function that describes my ball is a parametric function. If I already had a graph what is that shape? Except it's only the top half of that sphere, right? Because it's the positive square root. I don't want the bottom, I just want the top. That is already a function of two variables, isn't it? This is already f of x and y. So if I wanted to write a parametric description, I don't have to switch letters. I can keep using x and y. But my domain, where x and y live, is the circle of radius 3 in the xy plane. So that surface lives over the circle. Which means if I already have a function of x and y, switching to parametric forms isn't switching at all. It also means if I have a function of x and z, describe a function in y, right? I can leave it in x and z and write y as the equation. If I have a function in y and z, and I can think of it as a front, an x, I can do it that way. So if I already have a function of two variables, that's already parametric. We just didn't think of it that way. Back a long time ago, chapter 6, Calc 1, we did surfaces of revolution, right? And we did area of surfaces of revolution, right? That was in chapter 8. We did our ds this time, right? D capital S, to talk about surfaces. Well, it turns out I can even do surfaces really nicely. If I rotate a curve, I would get another copy of this function down here, right? And I would have circles like that. I go around the x-axis, I make a circle. And I would have one over here. I would have one over here, right? But that means I can figure out, depending on where I am, this is x, right? That's the x-axis. That means if I'm going around that, that part should be pointed out at me. I should have circles this way. Those are circles in y and z. So this time, to describe the surface, I leave x alone. I just go around, and that means I multiply by cosine of theta and sine of theta to make a circle of the right radius out along the x-axis. So surfaces, even surfaces of revolution, become easier. Whew. Questions? Back in chapter 14, we were finding tangent planes. We would have, remember me sticking the skewers in my hat, holding the cardboard in my head? We would find a derivative in each of the directions. And we would make a plane that was tangent to my surface. I want to do that here. How do I make a plane tangent to a surface if the surface is described parametrically? All right. Back in chapter 14. So this is exam 2. I had the equation for tangent plane. How did I find the equation for tangent plane? Now, big T was a tangent vector. That was on a curve. Plane. Tangent plane. Well, that's our tangent vector. Gradient went the wrong way. Gradient went along a surface, right? So that would be, how's the fastest down or the fastest up? This sticks out. Chapter 14, section 4. We found the equation for a tangent plane. We would write the partial derivatives. That gave us our normal vector, the one that stuck out of the plane. Or we could do the cross product to get the vector sticking out. But the important thing here is that we took these derivatives. And we took those derivatives because those were the grid in X and Y. Back in chapter 14, section 4, I have this picture of taking these partial derivatives on the curve. There, it's a little easier to see without the light. I have my surface in blue. I have the curve in the in the y direction. I have the curve in the x direction, and I take a partial derivative to get the slope of a tangent line. Make sense? I don't have a grid in x and y anymore on my surface. What grid do I have? there's my grid. My grid is in U and V, not in X and Y. So instead of taking my partial derivatives, in X and Y, I should do the same process, but I should do it in U and V. So what I need to do is I need to say, oh, the vector I need is made up of the partial derivatives. I need RU and I need RV. But those go along the surface, right? Those are in the surface. I need the vector that sticks out. I get the vector that sticks out. So the right normal vector, for my tangent plane is now RU cross RV. Instead of minus fx minus fy, 1. That's what we used back in chapter 14. But now I have a new grid, so I have a new tangent plane. An example. Let's go to the easy one we started with. Let's go to the cylinder. So remember, this is my shape. I want you to pick a point and build a tangent plane to the shape. And depending on where we are, that plane is going to look very different, isn't it? Let's do this calculation. What's RU? What's RV? Partial derivative time. Yes. What about RV? So to find the normal vector, I do the cross product. We seem to be going back to this formula over and over and over again. When I do I get these four, so that's 0 minus 2 cosine u minus j times these two. So I get 0, 0. That's convenient. Then I do k, and I get these two minus those two, so that's minus 2 sine u minus 0. Let's pick a point. I got to go back to the drawing I did at the very beginning. How about I pick this point right here? The point 2, 0, 0. Given my equation, what's the value of u at that point? What's the value of v at that point? The value of v should be really easy. The value of v. Value of v is 0. I want 2 cosine of u to be equal to 2. I want 2 sine of u to be equal to 0. What's the value of u? What was that, Jalen? I want the x value here to match the x value here. I want the z value here to match the z value here. What's the value of u? It's 0. Which means at this point, I can evaluate this. That's the normal vector for my plane. That normal vector is on my cylinder at the point 2, 0, 0, and it points this way in the negative x direction. That's sticking straight out of my plane. My plane is vertical. What's the equation for my plane? Oh, plane. This is our normal vector, n dot r minus r0 equals 0. What's r0? That's our point. Which gives me the equation of my plane, negative 2, x minus 2 equals 0. Or x equals 2. No matter what surface you give me, this is the method by which I find the equation of the tangent plane. Page 1116, example 9. Here's my surface. Looks like a really messed up folded wallet, doesn't it? We find RU and RV, we take their cross product. Given this point, that's where U is 1 and V is 1. So I can find the equation of the plane. Now, as long as the equation I get for my cross product isn't 0, then my curves won't have sharp corners. And that means that I won't have folds that are sharp edges. That's a smooth surface, like continuously differentiable curves were smooth curves. Questions? I'm about to make your life even more interesting. Surface area. We did the area of a surface, right? Again, back in chapter 14, we had the area of a surface was the double integral over the domain of the square root of 1 plus fx squared plus fy squared dA. But that square root comes from the little square area on our tangent plane, which means it came from these derivatives. In a parametric surface, I don't have those derivatives. Remember, by the way, we called this d capital S, just like we called the arc length one d little s. Well, if I'm using a parametric equation, then I use the partial derivatives, just like I did in the previous setting. And it turns out that the correct way to do this is to take the length of that vector we just found, which means there's going to be a square root in my problem. If these are not rigged, we are screwed. For the record, I took one of these problems that I did not make up. I stole it out of the textbook, and I shoved it into Wolfram Alpha, and it crashed. It said, this integral is not computable in the time allotted. I broke Wolfram Alpha with these questions. So it is very easy for these to get nasty. But as long as I have a smooth surface, then this calculation works. Page 1117. That's the formula we just wrote down. And if this is a parametric equation, that's great. If this is x and y, this becomes the same formula as this one. So these are actually the same equation. But now my area isn't x and y, it's u and v. Why am I doing this? It isn't for shits and giggles, people. I'm going to take my vector field. I'm going to move it through surfaces. How much is going through the bag in my vector field? How much is coming out? That's going to be a surface integral. We did surface integrals. If my surface is not a function, then it's got to be described parametrically. And in order to do that surface integral, I'm going to have to do this. That is next week. But there are 3 sections that are all related to this idea. And those 3 sections cover the next 2 major vector field theorems. And that means that I should do this as a separate piece. So Monday is question and answer day for these 2 sections, 5 and 6. We'll see you all then. Have a wonderful weekend.